Welcome back. Today we're talking about one of the biggest and most practical topics in neuroscience, control of movement. This is going to be from chapter 17 in our book, Neuroscience Fundamentals for Rehabilitation by Lundy-Ekman. So let's get started. Movement can look effortless. Reaching for a coffee mug, standing upright, taking a few steps across the room, grabbing your keys without looking directly at your hand. These actions feel automatic most of the time, but underneath that apparent simplicity is a highly coordinated system involving sensory input, motor planning, posture, balance, timing, force regulation, and constant error correction. So in this episode, we're going to walk through how movement is controlled, how the nervous system organizes different kinds of movement, how vision and somatosensation contribute to reaching and walking, and what happens when systems like the basal ganglia, cerebellum, upper motor neurons, or lower motor neurons are damaged. Let's start with a foundational idea: sensory contribution to movement control. Two key terms that we have to know here are feed forward and feedback. Feed forward refers to the anticipatory use of sensory information to prepare for movement. In other words, the nervous system is making predictions before the movement even happens. It is using prior knowledge and incoming sensory cues to get the body ready. Feedback, on the other hand, refers to the use of sensory information during or after movement to make corrections, either to the current movement that's happening or to future movements. A simple example is reaching for a glass of water. Feed forward is what allows you to shape your hand, orient your arm, and prepare your posture before you actually touch the glass. Feedback comes in once the movement starts, and especially once contact is made. The nervous system can adjust the trajectory, refine the grip force, and correct any errors. In normal movement, feed forward and feedback are constantly interacting. Feed forward consists of anticipatory motor impulses that prepare the body for movement, while feedback gives information about the state of the system so movement can be adjusted. Sensory input matters enormously here. In the absence of vision, reaching depends much more on somatosensation and proprioception to locate objects. If somatosensation is lost, as in a complete sensory deafferentation, positioning of the limbs becomes severely disrupted. In fact, loss of any of the three major senses that are integral to automatic movement interferes with the ease and gracefulness of movement. The three senses that are especially important for postural control and automatic movement include somatosensation, vision, and vestibular input. Before we get into more detail, let's organize movement into three broad categories. First, we'll have posture, which is primarily controlled by brainstem mechanisms. Then we have locomotor movement, which is primarily controlled by brainstem and spinal regions. In this chapter, the main locomotor example that we'll use is walking. And then we have reaching and grasping, which are primarily controlled by the cerebral cortex. Even though each type has a primary region associated with it, all regions of the nervous system contribute to each movement type. That's important. No movement system is truly isolated. Now, when we say locomotion, we're not only talking about walking, even though that's the primary example that we're using. It also includes things like crawling, creeping, jumping, running, skipping, and hopping. Let's focus first on postural control. Posture provides both orientation and balance. Orientation is the adjustment of the body and head to vertical. Balance is the ability to maintain the center of mass relative to the base of support. Postural control is achieved by central commands to lower motor neurons, but that output is constantly adjusted to the environmental context by the sensory input we are receiving. In order to orient to the world appropriately, the nervous system relies on three sensory systems. Somatosensation provides information about weight bearing and relative positions of body parts. Vision provides information about movement and visual cues for judging upright. And vestibular system informs a person about head position relative to gravity and about head movement. So if you think about standing on an uneven surface in a dimly lit room after spinning around, you can see how vulnerable posture becomes when one or more of these systems is compromised. Postural control depends on integration across all three systems. Let's move on to walking. Normal human walking requires contributions from all regions of the nervous system. The cerebral cortex provides goal orientation and control of ankle movements. That means the cortex helps determine where you're going and supports precise adjustments that allow walking to be functional, adaptive, and purposeful. The basal ganglia contributes in at least two important ways. Through the midbrain locomotor region, or MLR, the basal ganglia helps govern starting, maintaining, and stopping of stepping movements. Through the pedunculopontine nucleus, or PPN, they help adjust muscle tone in postural muscles. The cerebellum contributes timing, coordination, error correction, and balance control. The reticulospinal tract adjusts the strength of the muscle contractions through effects on lower motor neurons and reflex pathways. The vestibulospinal tract influences postural muscles. And in the spinal cord, stepping pattern generators control the pattern of lower limb muscle activation during walking or running. That means walking is not just a cortical decision to move forward. It is a multi-layered process involving automatic spinal patterns, brainstem postural support, subcortical regulation, cortical goal direction, and sensory adaptation. Sensory information is also used throughout walking to adapt motor output appropriately. So although gait may appear automatic, it still requires a lot of attention. This leads to the idea of dual tasks. One way to determine how much attention a person devotes to walking is to have them perform a second task while walking and observe what happens. If gait speed drops, stride frequency changes, or stride consistency worsens, that tells us that walking is drawing heavily on attentional resources. This is especially relevant in neurologic populations. Compared with neurotypical adults, people with disorders such as Alzheimer's disease, stroke, Parkinson's disease, vestibular disease, vascular encephalopathy, and idiopathic gait disorder tend to show greater deficits in gait speed, stride frequency, and stride consistency during dual task walking. So even though healthy adults walking often feels automatic, the nervous system is doing a lot of work behind the scenes to make it look that way. Now, let's shift to reaching and grasping, which depend heavily on the cerebral cortex. Two sensory systems are being utilized here: vision and somatosensation. Vision provides information for locating an object in space and assessing its size and shape. In reaching and grasping, the primary role of vision is feed forward. Vision is going to help plan the movement before it happens. If the movement turns out to be inaccurate, vision can also guide corrections during the action. The visual pathway, especially important here, is the action stream, also called the dorsal stream. This stream flows from the visual cortex to the posterior parietal cortex. The figure in the slides that we go over in class will also emphasize that the visual information traveling from visual cortex to posterior somatosensory cortex and then to the premotor cortex will help plan the movement. So this is the pathway that helps transform the I see the object into I know where it is, how big it is, and how I need to move my body in order to interact with it. Grasping is not just hand movement. It's coordinated with the activity of the eyes, head, proximal upper limb, and trunk. Orientation and postural preparation are integral parts of movement. Once an object is contacted, grip force adjusts quickly, which indicates feed forward control. But after the object is grasped, Somatosensory information helps correct any error in grip force. A helpful way to think about reaching and grasping is in phases. The slide showing the coin example breaks it down into 3 phases. Our first phase is going to be initiation, lasting from movement onset to maximum wrist velocity. The second phase is shaping, ending when the digits reach maximum opening. And the third phase is closure. That sequence tells us that each reach and grasp are coordinated but not identical. The hand doesn't just fly forward and randomly close. The nervous system times transport and hand shaping together in a very organized way. Now, let's zoom out and talk about the summary of normal motor control. From normal movements to occur, the motor planning areas, control circuits, and descending tracts must all act in concert with the sensory information to provide instructions to motor neurons. One of the most useful ways is to conceptualize this as a hierarchy of control. The flowcharts that are in your slides describes a decision level, and then below that, 3 levels of motor control. The top level plans and organizes the movement. The middle level specifies the spatial, temporal, and force parameters of the movement. And our lowest level produces the movement and corrects for minor movement errors. Sensory information is essential throughout the process. Even though, for simplicity, it may be omitted from some of the diagrams. Now, let's compare the basal ganglia and the cerebellum, because both are crucial to normal movement and contribute in different ways. The basal ganglia receive most of their input from the cerebral cortex and influence movement mainly by sending signals back to the cortex through the motor thalamus. Their circuits help control the initiation of movements and the amount of force used and when the movements start and stop. The cerebellum communicates with the brainstem, motor thalamus, and motor areas of the cortex through a different circuit. Its main role is to coordinate movements, ensure proper timing, and correct errors while movement is occurring. So, in simple terms, basal ganglia is going to help start, scale, and stop movements, while the cerebellum will help coordinate and fine-tune the movements. Both systems send information to the motor thalamus, which helps integrate their signals before movement commands are sent from the cortex. Now, let's look at the effect of sensory loss on motor control. If visual feed forward is lost, movement is impaired, and the person must rely more heavily on somatosensation rather than visual guidance. If there is parietal lobe damage, the action stream is interrupted, preventing accurate reaching and shaping of the hand. If proprioception is lost, even simple multi-joint movements become difficult to coordinate. During fast movements, this can lead to movement decomposition, where the person breaks a smooth multi-joint action into a sequence of simpler parts because the nervous system can no longer integrate the motion efficiently. And when complete bilateral vestibular loss happens, balance is significantly impaired. However, visual input or even touch information can significantly improve balance, which tells us nervous systems can sometimes compensate by leaning more heavily on the remaining intact sensory systems. Now, let's connect all of this to posture control and neurological conditions. In Parkinson's disease, there is muscle rigidity and reduced central control. Clinically, this can appear as a flexed posture, lack of protective reactions, and weak anticipatory postural adjustments. In hypotonic disorders, postural control is simply inadequate. The nervous system does not generate sufficient stability. With cerebellar lesions, the effects depend on the cerebellar region involved. Vestibulocerebellar lesions cause truncal ataxia. Cerebrocerebellar lesions do not affect posture, and spinal cerebellar lesions cause ataxic gait. Now, again, we're going to revisit walking during dual task. Walking, again, seems automatic. It requires a lot of attention, especially when we're doing another task at the same time. Research has shown that people with neurological conditions perform a dual task while walking. When people with neurological conditions perform a dual task while walking, their gait is impacted much more than in neurotypical adults. Specifically, they often show a decrease in gait speed, change in stride frequency, and less consistency from step to step. You will commonly see these in conditions like Alzheimer's, Parkinson's, vestibular disorders, vascular encephalopathy, and idiopathic gait disorders, like we mentioned earlier. But dual task walking can be a helpful way to assess how much attention a person needs to maintain a safe and stable gait. And finally, let's compare major signs of pathology in different motor system structures. When we have damage to our lower motor neurons, this will lead to flaccid paralysis, muscle atrophy, fasciculations, and hyporeflexia. Damage to our upper motor neurons directly causes paresis or paralysis and impaired selective motor control. Over time, subsequent adaptations, often grouped under the term spasticity, can develop, including contracture, reticulospinal overactivity, and hyperreflexia. Damage to the cerebellum is associated with ataxia, nystagmus, and dysarthria. And pathology in the basal ganglia is associated with either too little movement or too much movement, hypokinesia and hyperkinesia. When you step back, normal movement depends on a remarkable collaboration between many systems. The nervous system has to anticipate movement using feed-forward mechanisms, monitor movement using feedback, maintain posture and balance, coordinate locomotion, integrate visual and somatosensory information for reaching and grasping, and continuously refine output through circuits involving the cortex, cerebellum, basal ganglia, brainstem, spinal cord, and sensory systems. When any one part of that network is disrupted, movement changes. It may become slower, less accurate, poorly timed, poorly scaled, unstable, or effortful. And that's exactly why understanding the control of movement matters so much in rehabilitation and clinical practice. It helps us move from simply noticing when someone has trouble walking or has poor coordination, and instead identify which systems may be contributing, what kind of deficit is present, and how intervention can be targeted. That's it for today's episode on control of movement. If you can understand feed forward, feedback, posture, walking, reaching, and grasping, the role of the basal ganglia and cerebellum, and classic signs of major motor system lesions, you've got a strong foundation for understanding both normal movement and movement disorders. Thanks for listening.